All right. Good afternoon, everyone. Welcome. My name is Davor Bonaci. I'm a software engineer at Google, and I'm also serving as the chair of the Apache Beam Project Management Committee. And I'm going to give you today a technical introduction to Apache Beam. So Apache Beam is an open source project for expressing both batch and streaming data processing use cases. So when you use Beam, you are focusing on your logic and your data without letting the runtime details leak through your code. So basically with Apache Beam, with its clean APIs, you are defining your data processing pipelines completely separately from an engine that will execute it. And this separation allows Beam pipelines to run on many existing runtimes and many existing engines that you all know and love, like including Apache Spark and Apache Flink, Google Cloud Dataflow, and others. And to put Beam into the context of the broader big data ecosystem, let's talk a little bit about its evolution. So Apache Beam traces its roots back to the original MapReduce paper that Google published back in 2004 that fundamentally changed how we think about distributed data processing. At the same time, after 2004, Google kept building internal systems that supported Google Search and other systems within Google, and occasionally published papers about them. And that all changed somewhere around 2014, when Google started opening up its technology to the wider world, and first starting with its own cloud customers. So in 2014, Google launched Google Cloud Dataflow, which included a new programming model and a fully managed service for executing big data pipelines. At the same time, the open source community built their own MapReduce implementation in Apache Hadoop, and this whole ecosystem was born. And for this ecosystem, that's why we are here today. So Apache Beam is an effort to unify these two branches together. So it was seeded with original code from Google Cloud Dataflow and got started about a year ago. In that year, the Apache Beam community generalized it and integrated it with the broader ecosystem. So today, Apache Beam works with many of the open source tools and on multiple cloud providers. So today, I'm going to talk a little more about two key pieces of Apache Beam. First is its programming model that intuitively expresses data parallel operations, including both batch and streaming use cases. And then the second thing I'm going to talk about is its portability infrastructure, which lets you execute the same Beam pipelines on multiple runners. At that point, we are going to get a little more concrete, and I'm going to demo the same pipeline running on multiple engines. So that's going to be a little bit fun, kind of running a large-scale demo in a live setting. And then hopefully I'll end with a few pointers for getting started with this project. If you take away one thing from this presentation, it is this. It's this sentence. Apache Beam is a unified programming model designed to provide portable data processing pipelines. Two things, unified and portable. It is also efficient, but I'm not going to get to that argument in this talk. So let's start with a brief overview of the Beam model. So to really explain a programming model, let's think of a good use case that we are going to be building upon. So let's assume that we are building a mobile game. On that mobile game, our users are playing a game, they are scoring some points, and those points are coming back to our system. Let's say that users are organized into teams, and we are interested to find kind of team results. Right? It's simply summing up individual scores within that team. So let's start with that. So this diagram shows some points being scored. So the first point being scored is 5, and then 9, and then 7, and so on. Each of these scores occurred at a particular point in time. That event happened at some point. We call that event time. So there is also separate notion of a processing time. That is sometime after the event happened that our system got a chance to process it. So in the ideal world, all events would actually lie along this dashed line, meaning the processing time equals event time. However, distributed systems are really distributed, which means arbitrary delays. So some events in the system are processed around the time they happened, like this event number 3 that happened somewhere around 12:07 and got processed around 12:07. But this event number score of 9 happened around 12:01 but got processed like 7 or 8 minutes later around 12:09. So maybe the user played the game in an elevator or 3 levels underground in a garage and basically got a few minutes delay of that event getting into our system. So if you are really building a massive scale system that can process real-time data, these are the things that we really need to think about. So this is a hard problem, but to make it a little bit tractable, we are really focusing on separating the problem into 4 distinct questions. We are trying to give clean APIs that separate these 4 notions. The first notion is what results are being calculated. So this is really your business logic. Are you doing sums, joins, histograms, machine learning model? This is really your own custom business logic that doesn't really change in what kind of environment do you run your code. The second question is where in event time are results calculated. If we are going to build a system that runs over infinite time, we really can't calculate over the infinite data set, right? We have to somehow narrow it down to tractable chunks of event time. Then the third question is when in processing times are results materialized? Does the time each element arrives in the system affect the results? How do we know when to emit results? And finally, how do refinements relate? If we need to produce multiple results for a given window of time, how do those individual results relate to each other? And we are going to see how does this really work in practice. So I'm going to start with a really simple example of the first question, what is being computed? And here we have an input. We are applying a transformation to that input that is summing integers per key. So kind of the input to this program is a collection of events in the terms of key value pairs. The first is the team, the second is the score, and we are summing those integers per key and storing results in another collection. So this is our business logic. It's really simple, but it can be as simple as summing integers or as complex as complex machine learning models. And this kinds of computation won't really matter later on. We'll see that. So this is going to be our running example, and this looping animation will show what the system will do with this code. So we see the system summing up events over whole of event time as the system goes more and more through processing time. So the final sum of all these events is 51. As we see more and more events, we keep the trailing sum in an intermediate state, and we finish up overall data, producing the result 51. So this is really simple batch processing. We have our data available to us. We are going through our data, summing up integers, producing results. Very simple batch use case, irrespective of what the underlying algorithm may be. Now, let's start building up more and more complex pipeline. So let's start playing a little bit with event time. So we do have to specify event time if we ever are going to come to a full real-time system that can run on infinite data set. And here, we are specifying to the system that the input should be windowed into fixed windows of a given duration, right? And by doing so, our business logic does not change, irrespective of how simple or how complex it may be. Now let's see what does that do to the same example that we did before. So instead of producing one result, we are going to produce 4 results for 4 distinct chunks of event time. So instead of having one sum that is 51, we have 14, 22, 3, and 12. Right? These are the correct sums, and we are still processing the data along the processing time, and when we finish processing all the data, we emit results for the entire collection. Okay? So this is still not a streaming pipeline. This is just a windowed batch. We have all the data, we chunk it into pieces. Once the all complete processing is done, the results are available to us. Now, we'll keep adding complexity to this pipeline, and we are going to play a little bit with the latency of results. So what we are doing right now is asking the system to produce results based on the system's best estimate for a given window. When the system believes there will be no more data for the given window, right? This is obviously going to be a heuristic, and we're going to see what does this mean. So right now in this same picture that we have as before, we have one new squiggly line. We call that line a watermark. The watermark really represents the system's best estimate, what has been processed fully so far, right? For a given time, for a given point in processing time, what is the cutoff that the system believes that all elements in event time are being completely processed? And then, when the watermark passes the end of the window, the system produces results. So we see like around 12:06, the results are produced for the first window that ends at 12:02. And the result is 5, which happens to be incorrect. But for all other windows, the results are correct. So this is a case where the system was wrong, and the watermark was too fast for one window, and was just about right for the remaining 3 windows. So this is something that we can see in practice when we are running these kinds of pipelines at scale. So obviously there is some kind of tension here. If we make the watermark too aggressive, we will miss more and more elements. If we make it too slow, we'll just increase the latency of producing results. So it's a kind of, it's a little bit tricky to produce the right watermark. But however we produce it, we still have to account for late elements. Now let's see how a more sophisticated trigger can help us deal with late elements. So I'm going to modify the same pipeline I've been doing before. We are still producing the elements when the watermark passes the end of the window. But in addition to that, we are producing a correction, an updated result every time we see a late element. And in addition to that, we are also producing early, incomplete results so that we can see where the sum is trailing to, maybe. And we are asking the system to produce early results every minute. And then finally, we are asking the system to compute the results in an accumulating mode, which really means that the final result is what we actually want. So let's see how does this look on the same diagram. So the picture gets a little bit more complicated, but we see like for the first window, we have the result of 5 when the system believes that the whole elements are processed. And then when the system encounters element 9, that there is a late, for late element and the late firing and correcting the sum from 5 to 14 for the first window. And then there are no more late firings for any other window because the system wasn't wrong in any other case. But for example, for the second window, we see multiple early results as we ask the system. So first early result is 7, then 14, and then a final sum of 22. Right? At this point, we built a really complex real-time system. So it's a system that can run on an infinite input, a system that can produce early, speculative, incomplete results, a system that produces its best estimate as early as it can, and then finally corrects itself every time a really late element arrives. Right? So this is a really complex streaming system. And we were able to achieve all that without ever changing a single line of our business logic, irrespective of how simple or complicated it may be. Right? In this case, we are just summing integers to really understand what's going on, but this can be arbitrary complex logic. So this is really what unified model of Apache Beam really is. We took a single algorithm, in this case, an integer summation, and we tweaked a few lines of code to cover a wide variety of scenarios, from classic batch to a complex streaming pipeline. Just a few lines of code, irrespective of the business logic. And just like the MapReduce model fundamentally changed the way we think about distributed data processing, we believe this model, the Beam model, will change the way we unify batch and streaming use cases into a single unified model and API. All right, so that kind of covers what Beam can do, what it can express. Now let's talk a little bit about where it can execute and how it executes. Let's talk a little bit about portability. So at the heart of the Beam project is its model. We offer multiple language-specific SDKs for constructing a Beam pipeline. As you know, developers often have strong opinions about their language of choice, and we really want to meet them where they are. They should be able to write a pipeline in the language of their choice. And then there are multiple runners. And runners allow us to execute Beam pipelines on a variety of distributed processing engines. Right? This allows the user to choose the environment that's right for them. It may be on-premise or in the cloud. It may be open source or not. It can be fully managed or not. And it may change over time. We can run the same pipelines on multiple engines or change our mind 3 times a day if we really want to. And then finally, each runner needs to call back into user code, and that user code is written back in its own language. So Apache Beam provides really modular APIs for the runners to call back into specific language in a very efficient way. This is the vision. The reality is a little bit different, but not that different. So today, we have 2 SDKs, one in Java and the other one is in Python. And Java SDK can run on Apache Apex, on Apache Spark, on Apache Flink, on Google Cloud Airflow, and currently in development is a runner for Apache Gear Pump. In addition to that, we have several runners in exploration phase. That includes Apache Storm, Twitter Heron, Apache Samza, and a few proprietary ones. On the other hand, Python SDK runs on a much more limited set of runners today, but that part is being worked on. And we are finishing up our cross-language infrastructure in a way that even a single pipeline can be built by mixing and matching transformations from multiple SDKs. Stay tuned for that. Okay, so today I'm going to take a look at 3 specific runners out of all the runners that we have. So those are Spark, Flink, and Dataflow. And these were the original 3 runners in the Beam project, and also the 3 runners I'll be demoing today. So many of you are probably familiar with Apache Spark. It's a very popular choice today. It really excels at in-memory and interactive computations. Apache Flink is a little bit newer to the broader big data scene, but it got really good and clean semantics for stream processing. And then finally, Cloud Dataflow is a fully managed service in Google Cloud Platform for data processing that evolved from those years of internal work at Google. So how do we really provide an abstraction layer from these different types of runners? You know, maybe we do a lowest common denominator of all of them. And this is kind of the most common question I get asked. Is Beam really a lowest common denominator? The answer is, of course not. This would be way too limited. This would be way too narrow. Or maybe is Beam a union of all runners? Not really, right? This would really be a total mess of a system, right? So Beam really tries to be at the forefront of where the data processing is going. It provides its own abstractions, its own layers that translate back into runners, that compile into individual runners. So kind of, we are both pushing functionality into the runners and pulling data processing patterns out of the runners, right? So I'll give you just a couple of examples. So keyed state is an example of functionality that existed in various engines, primarily Flink, for a while. And it is a really interesting and a common use case. And it was only recently added to Beam. And then there is also the vice versa argument, right? We see a clear evidence that Beam is influencing the roadmap of other projects. And you know, one example is Flink's data streams API that were quite heavily influenced by the Beam model. Right? But does that mean then that every pipeline runs on every runner? And the answer is kind of. If you are using standard capabilities in Beam, chances are that pipeline runs on all runners. But if you are using something that was added yesterday, chances are that runs only on a smaller number of runners, but still several. And we are trying to be very upfront about it, and we are publishing a capability matrix, where we are listing a Beam functionality and kind of the support for that in each runner. And for example, if you are doing more standard batch use cases, that kind of pipeline will run anywhere. And if you are using maybe very advanced streaming APIs or a streaming use case, that may run on a fewer than all runners. Okay, so with that behind us, let's take a look at a live example. So give me a sec over here. Okay. Come on. Okay. Okay, sorry about that. We'll look at, so I'm going to run a pipeline, and this is the full pipeline code that we are going to run. So this is a main program of Java. it's a main function of a Java example. We are constructing a pipeline and then applying several transformations. First, we are reading something from a text file, parsing events that we read from a text file into a more convenient data structure. And then we are setting the timestamp of those elements based on what we read for each particular element. Then we are windowing that into fixed windows of duration of 1 hour, and then doing all our business logic that resides in calculate team scores. So this is our transformation that contains our business logic. So this is a simple batch pipeline. And if we look at in more details about parse event function, so we are just parsing events, we are separating the lines based on a comma, and we are introducing a counter called parse errors. So maybe we are kind of guarding ourselves against bad input here. And then this is our calculate team scores that we are applying over here. So it basically has our familiar sum integers per key, and then we are writing that back to a file. So I'm going to run that pipeline on multiple runners. So I'm going to start with Cloud Dataflow. Give me a sec. Let's see. Okay. So this is this pipeline running on Cloud Dataflow. I ran this pipeline last night, and you can see that this pipeline, the Google Cloud Dataflow UI, is visually displaying the pipeline as we have built it in the